Think about the phone in your pocket right now. If it's an iPhone, it runs on Apple's highly specific software, built with their own proprietary coding languages. Now compare that to the machines it talks to. When you search the web, your phone is pulling data from massive server racks, like this early Google setup, running completely different operating systems, written in entirely different languages. If every tech company invented their own custom way to send messages back and forth, a browser built by one team wouldn't understand a server built by another. Developers would have to write thousands of unique translations just to load a simple web page. To build a global network, all these different machines needed a single shared agreement. They needed a common language that everyone agreed to speak, regardless of who built the hardware. HTTP, or Hypertext Transfer Protocol, functions as a rigid set of rules for how clients and servers talk to each other. Rather than a piece of software you download, it's a mutual agreement on how to behave. You can think of it like the rules for sending a letter through the postal service. To guarantee delivery, every piece of mail has to take on a highly specific, predictable shape. The post office doesn't care if the letter inside is typed, handwritten, or in another language. They only care that the envelope has a stamp in the top right corner and a destination address sitting right in the middle. HTTP works exactly the same way. As long as your computer packages its message into this exact expected format, the server on the other end will know exactly how to read it. Underneath all the slick interfaces we click and swipe every day, this protocol is actually incredibly simple. It's just plain, human-readable text. Looking at this diagram, we can see exactly how a real HTTP request compares to our physical letter. On the left is the raw text your browser actually sends, and on the right is our envelope. Those bottom lines of text are called headers. Just like the address block on our envelope, these headers tell the network exactly where the message is going and what kind of data the sender is expecting back. The very top line contains the method, in this case the word get. This is the actual request being made. It's the letter inside the envelope, politely asking the server to hand over a specific user profile. Keeping these instructions as plain text was a deliberate choice by the early architects of the web. It made it incredibly easy for developers to read the code, spot errors, and build new tools without needing special decryption software. Once that letter is sent, HTTP follows one very strict rule. Communication is always a call and response, and the client must always speak first. A standard web server is completely passive. It sits quietly and listens. It cannot spontaneously decide to send you a new video or an article out of nowhere. You have to ask for it. As we see in this diagram, when the server gets your request and finds the information, it packages up the actual data you asked for, organized into structured blocks of text, and sends it back. And on the outside of that return envelope is a status code. Here we see a 200 OK, which is the server's official stamp of approval, confirming the request was successful. This exchange, a request going out and a response coming back, is the basic mechanic for everything we do online. Every time you tap a link, submit a password, or refresh a feed, your device is quietly sending and receiving these exact letters. There is one catch to this system. By design, HTTP is what we call stateless. In practice, statelessness means the server has instant amnesia. The second it finishes sending that return envelope, the server destroys all memory of the transaction. You are completely forgotten. Because the server forgets you immediately, your browser has to remind the server who you are with every single new click. You have to include your login info or proof of who you are in every single letter you send. While that sounds incredibly repetitive, it is absolutely essential. By not having to memorize the history of millions of active users, servers are freed up to process new requests instantly, which is exactly what keeps the entire internet running at high speed. Over the decades, engineers have upgraded this system from version 1 to version 3. The core rules of the letter haven't changed, but the speed of the mail trucks has drastically improved. In this animation, we can see a major upgrade called multiplexing. Instead of sending one envelope at a time through a narrow tube, modern HTTP opens up a massive pipe, allowing dozens of requests and responses to fly back and forth all at once. But speed doesn't solve security. Because standard HTTP is plain text, sending a password is like mailing a postcard. Anyone handling the mail along the way can flip it over and read it. To fix this, we use HTTPS. The S stands for secure. It takes that exact same plain text letter, places it into an encrypted connection, and locks it inside before sending it out over the network. HTTPS preserves this standard letter format while keeping the contents hidden from prying eyes. While it's often mistaken for a programming language, HTTP acts only as the set of communication rules. It provides the protocol, not the logic you'd use to build an application. You build your actual website or app using languages like Python, Java, or JavaScript. HTTP is just the transport system you use to move that app's data across the world. No matter how advanced your code is or what new frameworks you use, your application still has to fold its messages into that standard postal envelope. This shared agreement means an iPhone in Tokyo can effortlessly ask a Google server in California for directions. It is the simple, rigid foundation that holds the entire web together. You click a button, a function fires, and the screen updates. To a user or a friend and developer, a network interaction feels instantaneous, but that perceived speed masks the series of distinct steps required to complete the exchange. The gap between a user's click and the resulting screen update is packed with hidden mechanics. We call this sequence the request-response cycle. It is the complete end-to-end journey of a single HTTP interaction, starting the millisecond a client sends a request and finishing the moment it processes the server's reply. Early in backend development, it is common to treat this cycle as an opaque black box. You send data out into the void, the server does some mysterious work, and a response comes back. This diagram shows what sits between the client and server, a strictly ordered, multi-stage pipeline. Every request must pass through specific gates in sequence. First, the client resolves its target's address and negotiates complex security handshakes just to open a connection. Only then can the physical transmission of the formatted HTTP data begin, traveling across miles of fiber optic cables and routing hardware. Once the data actually reaches the server, the application cannot run its core code right away. It must first parse the raw data stream and run layers of pre-processing security checks. Finally, the server executes the required business logic, builds a response payload, and ships it all the way back down the exact same pathway. Because latency spikes and network errors correlate to specific stages in this sequence, understanding the pipeline provides a diagnostic framework for the entire backend. To isolate where those failures happen, we start at absolute zero on the client device. An HTTP request cannot travel over the network until it knows exactly where it is going. This timeline charts the life cycle of a request in milliseconds. The cycle begins with DNS resolution, translating a human-readable domain name into an actionable IP address, claiming our first block of processing time. With the IP address in hand, the client must establish a reliable pathway to the server. This requires a TCP handshake, a multi-step negotiation that forces data to travel back and forth across the network several times. The client initiates this by sending an outgoing synchronization request, asking the server if it is available to talk and open to receiving data. The server receives this request and, assuming it has the available resources, sends an acknowledgement back across the network to the client. The client then sends a final confirmation message back to the server, successfully locking the connection open for continuous communication. If the connection is secured via HTTPS, which is the modern standard, the devices must execute a completely separate TLS handshake to establish encryption keys, compounding the setup delay. Notice that we are several network round trips deep into our timeline, and the actual HTTP request data has not even left the client device yet. A significant portion of request slowness originates purely from this network setup latency, occurring before a single line of backend code even executes. Fast forward to the exact moment the server's listening process accepts the connection and begins reading the incoming stream of ones and zeros. A common assumption is that the server instantly triggers the application code to retrieve data. In reality, the server is looking at a raw text stream, and it must translate that text before it can do anything useful. This diagram details the parsing stage. The server takes the raw HTTP text block and algorithmically chops it into distinct, actionable variables that the application code can actually read. First, it extracts the HTTP method, like GET or POST, and the URL path, so the application knows exactly which internal function to trigger. Next, it extracts the header metadata, pulling out details about what type of device is making the request and what data formats it can accept. Finally, if the request includes a body payload, like a user submitting a form, the parser extracts and formats that specific chunk of data. These parsed variables are then fed into the middleware layer. This is a critical gauntlet of pre-processing checks that run immediately after parsing, but strictly before the core application logic. For example, a piece of authentication middleware will intercept the request, extract a security token from the headers, and validate the user's identity before allowing them deeper into the system. A separate piece of middleware might record the request's IP address for system-wide logging, or check a rate limiter to ensure the user isn't spamming the server. Isolating these tasks into a dedicated pre-processing pipeline allows backend engineers to centralize security rules. You write your authentication logic once in the middleware, rather than copying and pasting it across hundreds of different endpoint functions. After surviving the middleware gauntlet, the request finally hits the core business logic. This is where the application queries databases, runs calculations, and enforces specific business rules. Backend developers spend the vast majority of their time writing, optimizing, and caching queries at this specific stage to minimize server processing time. Once the logic finishes executing, the server completes its internal work by constructing the outgoing HTTP response, packaging requested data alongside a success status code. This diagram maps the HTTP cycle as a diagnostic decision tree. When a system breaks, professional engineers use this exact sequence to locate the failure. A failure at the very first stage instantly isolates the problem to external routing. If DNS fails, the client device throws a distinct server not found error without ever touching your infrastructure. If the connection fails during the TCP or TLS handshakes, it results in a timeout or a connection refused error, heavily pointing toward a strict firewall or a closed port on the server. If the server crashes mid-processing or encounters a fail bug in the logic core, the network connection itself succeeds, but the client receives a 500-level server error. And if the network simply drops the connection while the response payload is traveling back, the server will have executed its job perfectly, but the client will only receive partial or corrupted data. Treating the HTTP cycle as a diagnostic map turns backend debugging from panicked guesswork into a systematic process. You look at the specific error type to isolate exactly which gate in the pipeline failed to open. Assuming all stages succeed, we pull back from the server internals to track the newly constructed response as it travels back across the established network connection to the client. The client device receives the payload, parses the success status code, reads the body data, and finally updates the user interface on the screen. This reveals the fundamental constraint of standard HTTP protocol design, its strictly synchronous nature. This diagram shows the core limitation of standard HTTP. From the server's perspective, one request mandates exactly one response. Once that response finishes transmitting, the transaction is functionally over. There is no inherent mechanism in standard HTTP for a server to spontaneously push multiple unprompted messages or updates to a client. It only speaks when spoken to. Recognizing this synchronous limitation dictates architectural choices. It clarifies when standard HTTP is sufficient for a project, and when developers must upgrade to asynchronous, continuous protocols like Websockets to build real-time applications. However, there is one final misconception to clear up. Just because the request-response transaction is over does not mean the physical network connection is immediately destroyed. In modern HTTP implementations, systems utilize persistent connections. The established TCP pipeline is intentionally kept alive and waiting for further instructions. This massive performance benefit keeps the pipe open, bypassing severe DNS and handshake latency for future requests. When a user clicks a second button, the new request shoots rapidly through the open pipe, arriving in a fraction of the time. A third request can follow seamlessly right behind it, maximizing the efficiency of the established pathway. Managing how data moves through this strict, latency-bound pipeline is just as critical to backend engineering as writing the core logic functions themselves. To truly optimize this cycle, you must dissect exactly what kind of data is actually traveling inside the pipeline. That requires breaking down the precise anatomy of HTTP headers, bodies, and parameters. Millions of times per second, clients and servers exchange dense packets of information to keep the modern web running. Behind every polished application interface, this massive exchange of data relies on the transmission of raw text over a network. A single request carries a heavy operational burden. It must simultaneously provide routing instructions, supply security credentials, declare processing rules, and deliver the actual data payload. When sent as an unformatted stream, this complex mix of information fails upon colliding with the server. If mixed into an undefined blob, the server cannot parse it. To solve this, HTTP enforces a rigid architectural structure. What you are looking at is a complete, real-world API request. Over the next few minutes, we will deconstruct it layer by layer. To ensure flawless parsing between machines, HTTP divides every communication into a strict three-part anatomy: parameters, headers, and the body. We begin with the top line of the code, which governs routing. Looking closely at this section, we see the target destination. The 42 here is a path parameter. It acts as a mandatory identifier that tells the server exactly which specific resource to target in its database. In a physical delivery system, the path parameter is the exact street address of a specific house. It's strictly required to make the delivery happen. Right next to it, appended after the question mark, is an entirely different type of instruction. These are query parameters. They act as optional modifiers for the request. Query parameters do not change where the request is routed. Instead, they tell the server how to process it, in this case, triggering a notification email, though they are also commonly used for sorting or filtering a list of results. An identifying path parameter locates the resource, while a modifying query parameter shapes the result. Confusing the two disrupts standard RESTful routing logic. Moving to the middle block, we find headers, formatted as key value pairs. Think of this as the shipping label. The content type header declares the payload's format, writing package format JSON on the label. Below, the authorization header provides security tokens, logging sender credentials. Headers act strictly as metadata. They instruct the receiving server on exactly how to interpret, process, and handle the incoming transmission. You will also encounter custom header parameters, like an XRequest ID. These carry specialized configuration values used for internal operations, like request tracing across multiple servers. The server reads this metadata to validate the request rules before it ever attempts to process the actual contents of the delivery. The headers describe the request and the sender, but they never contain the core data payload itself. Directly below the headers is an empty, blank line. This physical blank space in the text is a hard architectural boundary in the HTTP specification. It definitively signals to the parser where the metadata ends and the real data begins. Past that boundary is the body block. The JSON code shrinks down and drops into the box. The body is the actual data payload. This is the real content transferred across the network to create or update a specific record. The server only knows how to successfully unpack and read this JSON data because the content type header on the outside label provided the precise instructions to do so. These anatomical divisions are strict HTTP rules. Violating them will break automated tooling and cause immediate server errors. This brings us to a common anti-pattern, trying to attach a data body to a GET request. GET requests are designed exclusively for retrieving data using path and query parameters. Standard servers will outright ignore a body payload attached here. Another major anti-pattern involves attempting to hide security credentials inside the body payload instead of placing them in the headers. If a token is locked inside the box, the scanner reads the label, finds no credentials, and drops the request in the trash. Gateways check headers first to save power. Hiding tokens in the body violates the expected flow, causing immediate rejection. Predictability is the operational foundation of network security and routing. Deviating from these conventions forces downstream developers to account for non-standard behavior, leading to fragile and error-prone integrations. Returning to the HTTP request, the architectural zones are completely mapped. Path parameters locate the resource, while query parameters modify the action. Headers provide processing instructions and security metadata. Separated by a hard break, the body delivers the precise data payload. This strict formatting is exactly what allows millions of complex instructions to flow through server gateways without error. Mastering this request anatomy allows backend engineers to build and consume APIs that are predictable and compatible with standard automated tooling. With the data structure firmly defined, the logical next step is to determine the exact actions the server should perform on that data. That requires a vocabulary of foundational verbs: get, post, put, patch, and delete, the HTTP methods that bring this anatomical structure to life. Early web APIs had a massive structural problem. To perform actions, developers invented new endpoints, resulting in commands like /delete user. This custom vocabulary made routing bloated and unpredictable. By standardizing the approach, we drop the verbs and identify only the resource, like /users/42. This is the core solution of RESTful architecture. It decouples data identity from operational intent. The URL acts as a noun, targeting the resource. The HTTP method acts as the verb. By swapping the method, we change the operation without modifying the URL text. These 5 core verbs, get, post, put, patch, and delete, form the foundational vocabulary of all modern backend development. These methods function as strict mathematical operations applied directly to a server state machine. To build resilient architecture, you have to look past the names of these verbs and understand the strict system state rules that govern them. These rules dictate how the entire internet handles data. Browsers, proxy servers, and routers constantly process millions of requests. They don't have the computing resources to open up and read the payload of every single one. To make routing decisions blindly, they rely on 2 critical constraints built into the HTTP methods themselves: safety and idempotency. Safety is an absolute guarantee that a method will not alter or mutate server-side data. If an operation is marked as safe, you can execute it once, or you can execute it 1,000 times in a row, and the underlying database will remain exactly as it was before the first call. Idempotency is a mathematical guarantee regarding the end state of the system. It dictates that repeating a specific request multiple times yields the exact same server state as making that request just once. These constraints allow browsers, CDNs, and retry mechanisms to operate autonomously without risking database corruption. The GET method is the primary operation for retrieving data, and it is completely bound by the rule of safety. This diagram illustrates a server database storing structured data. When a GET request hits the block, a copy of the data is extracted and returned to the client. The original block remains completely untouched. Because a GET request never mutates state, any parameters needed for the request must be passed through the URL path or query string, never tucked inside a body payload. This safety guarantee provides a massive architectural advantage. Because GET requests cannot alter data, intermediate layers like content delivery networks can aggressively cache the responses. When 10,000 users request the same product page, the CDN serves the cached copy. The central server is protected from being overwhelmed by repetitive read operations. Mapping a state-changing action to a GET request is a frequent error made by developers attempting to save time. Automated tools like web crawlers or browser prefetchers constantly fire off GET requests to index links, operating on the strict assumption that they are safe. If you wire a delete command to a GET endpoint, a web bot crawling your site will unintentionally wipe out database rows just by reading the page. Keeping GET requests strictly safe is a structural necessity to prevent automated systems from corrupting your data. To create new data, we use the POST method. Unlike GET, POST violates both safety and idempotency. POST changes the state of the server. It carries its payload directly in the request body and uses it to generate a brand new resource. It creates novel state where none existed before. The critical vulnerability here is that POST is not idempotent. Repeating the command compounds the effect. If you send the request twice, you get 2 distinct resources. This timeline diagram illustrates a network failure scenario. A client sends a POST request. A timeout occurs, so the system automatically sends a second, identical POST request. On the server side, 2 completely separate order blocks are spawned side by side. The user only wanted to buy 1 item, but the network lag triggered a duplicate record. In e-commerce, this translates directly to double charging a customer. Because POST is inherently dangerous to retry, intermediate network layers are programmed never to automatically repeat it when a connection drops. To safely process financial transactions using POST, distributed systems require secondary engineering safeguards, like idempotency keys, to prevent this exact volatility. We need a way to modify data that is safe to retry. The put method is a state-changing operation that solves the automatic retry problem because it is strictly idempotent. Put updates an existing resource by completely replacing the entire object with the exact payload provided in the request body. This visualization shows a database record containing name, email, and age fields. Because put is an absolute overwrite, it is safe to retry. Sending the exact same payload 5 times in a row simply stamps the same data over the same location, resulting in the exact same final state. If an incoming put request only contains a new name value, the server replaces those missing fields with null values, purging the existing data. To solve this data loss issue, HTTP provides the patch method. When a patch request containing only an email value hits the database, it executes a partial update. Only the email row updates. The name and age rows remain perfectly intact. The patch method explicitly modifies only the specific fields provided in the incoming payload, leaving the rest of the original object entirely untouched. However, unlike put, patch is not strictly guaranteed to be idempotent by the HTTP specification. If a patch request acts as a relative change, for example, instructing the server to increment the balance by $100, sending that request 3 times adds $300. It compounds the state, acting just like a post. Choosing between put and patch requires deciding between demanding absolute idempotent state replacement or allowing surgical but potentially volatile updates. The delete method is the final core action. It destroys state on the server, and it does so without utilizing a request body. The exact resource to be destroyed is specified directly via the URL path parameter. Because delete alters data, it violates the rule of safety, but it is classified as idempotent. This often confuses developers. How can you repeatedly destroy data without causing compounding system errors? The mechanism works like this. The first execution successfully targets and destroys the node. If a network drop triggers a retry, the second identical request arrives at the exact same location, finds it empty, and simply dissipates. It doesn't alter any surrounding data. The server might return a 404 not found error to the client on that second attempt, but the structural integrity of the database remains exactly as intended. The resource is gone. Idempotency is defined exclusively by the absolute consistency of the system's final state. The success or failure codes returned to the client are secondary to the consistency of the data. This matrix categorizes get, post, put, patch, and delete. Mapped against safety and idempotency, they form a universal contract. When applied to physical infrastructure, traffic flows from a client through a security layer, a proxy cache, and finally to the core server. The proxy layer blindly trusts the HTTP method to make its routing decisions. It immediately absorbs GET requests and serves them from the cache, while it forces state-changing methods like POST and PUT to bypass the cache entirely and hit the server. Security appliances rely on this exact same matrix. They specifically flag POST, PUT, and delete requests, subjecting them to strict cross-site request forgery validations. GET operations are allowed to bypass these heavy security checks. By definition, a safe method cannot be used to forge a state change. Mismatched HTTP methods break caching logic and bypass standard security protections, making the resulting architecture inherently fragile. The HTTP specification does include a few specialized edge case methods, like the head method, the options method, and the trace method. These handle specific tasks like diagnostic loopback testing and CORS validation, but those are specialized tools. Get, post, put, patch, and delete form the immutable, everyday vocabulary of the web. Aligning your backend code with these exact verbs separates fragmented, custom-built logic from truly resilient distributed architecture. Backend engineering is the science of predictable intent. By aligning with these semantics, developers ensure the global internet understands exactly what their API is built to do. When a client talks to a server over a stateless protocol, it is essentially sending data into a void. It transmits a request packet to the server, but the packet that comes back returns completely blank. This creates a diagnostic problem. Did the request succeed? Did it fail? Or did the server crash? We could force the client to open the payload and parse the actual response body just to see if an error message is hidden inside. But doing this for every single transaction wastes bandwidth and compute power. To fix this, HTTP splits the returning packet into two distinct blocks. You have a smaller header section on top, completely severed from the body below. Inside that isolated header sits a 3-digit number. This HTTP status code acts as an out-of-band signal, operating entirely outside the payload. These codes provide a universal, language-independent layer of metadata. Regardless of what programming language a system uses, they all rely on these numbers to communicate the exact state of a transaction. These digits form a rigid diagnostic taxonomy. They cleanly separate the network state from the application's business logic. This matrix shows the overarching architecture of HTTP status codes, grouped into 5 categories. The first digit tells the client the outcome. The 100s are informational, and 300s handle redirections, so we will set them aside. The 200s are the success category. Any code starting with a 2 tells the client its request was successfully received, understood, and processed. The most common is 200 OK, the standard success signal when retrieving data. But returning 200 for everything is a mistake. Inserting a new database record returns 201 created. Deleting a resource with no data to return signals 204, no content. Collapsing all these outcomes into a generic 200 destroys clarity. Precise success codes tell the front end exactly how to manage its internal state. When requests fail, we hit the most important diagnostic boundary, the line separating 400s from 500s. The 400 block isolates client faults. If you see a 4XX code, the client sent a request that was malformed or logically impossible. This includes syntax and routing failures. If the client sends invalid JSON, the server rejects it with a 400 bad request. If the client asks for a URL that doesn't exist, it gets a 404 not found. It also covers operational mistakes, like a 405 method not allowed or 409 conflict. The 500 block is entirely different. Here, the client sent a valid request, but the server itself fails while trying to process it. This could be a generic application crash, triggering a 500 internal server error. It could also be a proxy failure, resulting in a 503. This single-digit distinction dictates fault attribution. It tells an engineer where to start debugging. Look at the payload for 400 or backend logs for 500. Within the client fault category, there is a common point of confusion, 401 versus 403. Looking at this matrix of identity and permissions, 401 unauthorized is strictly an authentication failure. The server has no idea who the client is. Conversely, 403 forbidden is an authorization failure. The server recognizes the client's identity, but explicitly denies them permission. Getting this wrong breaks application flow. This distinction dictates whether the client should route a user back to login or display an access denied page. To lock in this diagnostic taxonomy, we can map these definitions to a physical environment, like ordering at a restaurant. The 200s are smooth operations. A 200 OK means your food arrives exactly as ordered. A 201 created means you successfully secured a reservation. A 400 bad request is speaking gibberish to the waiter. A 404 not found is demanding a dish that has never been on the menu. The security codes map neatly as well. 401 is trying to enter a VIP club without showing an ID at the door. 403 is showing a valid ID, but discovering your membership tier doesn't grant you access to that section. Finally, a 500 internal server error means your order was perfect, you had the right ID, but the kitchen caught on fire. Accurately classifying the error prevents wasted effort. If the kitchen is on fire, repeatedly asking the waiter for your food won't help. Developers map a status code for every endpoint outcome. A valid post request routes to 201 created. Missing fields terminate at 400 bad request. Duplicate data hits a 409 conflict. An offline database throws a 500 internal server error. It is important to note that a 200 OK only proves the HTTP request response mechanism succeeded. If you execute a search and get 0 results, the HTTP transaction still worked perfectly. The code is 200.
even if the application data isn't what the user hoped to find. Explicitly mapping complex business logic to this finite set of signals is what defines a resilient API. Status codes efficiently solve the problem of out-of-band signaling for single, isolated requests. The client always knows exactly how the transaction resolved. But this introduces the crucial architectural limitation of the HTTP protocol itself. The exact moment a status code is returned to the client, the server instantly resets. It forgets the entire transaction ever happened. Every subsequent request starts with a completely blank slate. The server retains absolutely zero memory of the successes, the failures, or even the identity established in previous exchanges. This unforgiving constraint is known as statelessness, and it forces engineers to solve the next major architectural challenge: how to make a system with severe amnesia maintain persistent user sessions.
Every network request is treated by the server as a completely isolated, independent event. This is the core defining characteristic of HTTP, statelessness. The strictness of this design is absolute. The server retains zero memory of previous requests. If you send two requests from the exact same browser, separated by a fraction of a millisecond, the server processes them as if they came from two total strangers who have never interacted before. Yet, as users, our experience on the web is entirely continuous. We log into applications and stay logged in. We browse e-commerce sites and build persistent shopping carts. This presents a paradox. If the foundational web protocol instantly forgets every interaction the moment it finishes, how can complex, continuous applications exist? Explaining how a continuous user experience survives protocol amnesia is a requirement for designing modern, scalable backend systems. To see how this works, we have to look past the user interface and examine the backend server architecture directly. Statelessness is a deliberately engineered architectural constraint rather than an accidental limitation of early networking. By stripping the server of the burden to remember clients, developers are forced to build decoupled, modular systems. The server doesn't have to check internal records or maintain a running history for every active connection. This constraint yields massive dividends in horizontal scalability and fault tolerance. When servers do not track state, you can add more servers to a network without them needing to constantly synchronize data with one another. Forcing absolute amnesia onto individual servers is the mechanic that allows the internet to function at a global scale. We can prove this by modeling the alternative. Let's look at exactly what happens when a server attempts to maintain a continuous memory of its users under pressure.
In a stateful system, every active client requires the server to dedicate a physical portion of its memory to store that user's context. This application scales linearly with traffic. 10 users take 10 blocks. 1,000,000 users require 1,000,000 blocks of continuous memory. The first failure mode is simple resource exhaustion. Under heavy load, the server crashes, exhausting its physical RAM trying to track the state of every connected client. Adding more identical servers is the standard solution for an overloaded system, but stateful systems resist this. If a user's context is trapped in the local memory of server A, then server B has no idea who that user is. If the network routes their next request to server B, the session breaks. To fix this issue, the system has to synchronize every client's memory state across every single server in the cluster. This introduces massive computational overhead, consuming network bandwidth simply to keep the servers in agreement. Stateful architecture limits system growth because server-side memory becomes a single point of failure. To solve this routing trap, HTTP takes an approach similar to a massive enterprise call center. When you dial customer service, you might reach a random representative who has no memory of any previous calls you've made. You establish continuity by providing a complete contact packet right at the start of the call, usually by handing over a specific ticket number. The representative uses that number to understand exactly what you need right now. Once they process that specific ticket, they hang up and forget the interaction, freeing up their cognitive load for the next random caller. This maps directly onto HTTP request routing.
A central load balancer sits in front of a cluster of identical servers. Because every request carries its own complete context payload, the load balancer can send any request to any server. No server needs prior memory to do its job. This architecture provides the foundation for failure resilience. If one server node hardware crashes mid-session, The load balancer simply routes the user's next request to a different node, which processes it using the context provided in the request itself. We can see this stateless theory in action within an e-commerce platform. If the backend immediately forgets a user after their first click, how does it process consecutive add-to-cart actions? The state has been relocated. The server never remembers the user. Instead, the client actively proves its identity on every interaction. During the initial login event, the server validates the user's credentials and issues a cryptographic key, typically called a token. This cryptographic token, such as a JSON web token, is mathematical proof of identity held entirely by the client device. The server does not store a copy in its active memory. When the user clicks Add to Cart, the browser initiates a separate HTTP request. It embeds the token inside the HTTP headers of the data packet. The browser attaches this proof automatically, without user intervention. The server receives the request and mathematically validates the token's authenticity. It verifies the math on the token rather than looking up a session ID in local memory. It approves the token, processes the cart update, and then drops the connection, returning to its default state of amnesia. Every subsequent click on the website generates a fresh, completely isolated request that runs through this exact same validation loop. The feeling of a continuous session is effectively an illusion, maintained by the client repeatedly flashing a cryptographic ID badge at a server that forgets them the moment the request is finished. Because the protocol is so strict, several engineering misconceptions have developed around where state is allowed to exist in a system. First is the database myth. Statelessness prohibits request-coupled memory on the application server, but it does not prohibit long-term data storage. You can write user data to a persistent database. The database handles that persistence outside the bounds of the isolated HTTP transaction occurring between the client and the server. Second is the cookie myth. Utilizing cookies does not change the nature of HTTP. Cookies are automated transport mechanisms. They are small files the browser uses to carry the identity payload forward. Regardless of whether you use a database for storage or cookies for transport, the core web server itself remains stateless, evaluating each interaction as an isolated event. While statelessness is the standard for RESTful APIs, deliberate architectural exceptions exist for specific use cases. Websockets are the primary example of an intentionally stateful, persistent connection between the client and the server. Websockets are reserved for features like real-time multiplayer games, where maintaining a continuous stream of two-way data is functionally required. The computational cost of persistent state is paid because the feature demands it, but this is a costly exception, carefully chosen over the default design of standard web APIs. Effective backend design leverages HTTP's default amnesia to achieve massive, resilient scale, while utilizing client-side proofs to maintain the illusion of continuity.